Right, okay. Students, can you all hear me? Yeah, good afternoon. Right, okay. Hmm. Right. So, today we are going to discuss about 2016 Visakha Vidyalaya paper, right? Remaining questions. But remember, students, there was a small issue in the last week recording. Okay. I think I forgot to put the recordings, but still I can remember that I put the recordings. And for you also, small request when you come to the class at the beginning, check whether I have put recordings. Okay, the recording now recording is ongoing, so therefore you also check if it is not recording. Tell me, sir, recording is not turn on, right? So last week actually I did record it, but anyhow something happened. I'll put that recording later, so no issue. So let's start from the question number one, part B. Ne? So this is that is the question we have discussed, right? So today, so the paper that we were discussing is 2016 Vishaka Vidyalaya. First term test, right? Okay, question number one, part B. Last week we completed the part A. Now today we have to discuss about part B. Following is a diagram shows transition of elements in between energy levels of hydrogen. So they have given the diagram related to the hydrogen emission spectrum. So that means this question is related to hydrogen emission spectrum, isn't it? So this question is related to the hydrogen emission spectrum that we discussed in the first unit, right? So they have given the line diagram. So this is actually n equal infinity. Line also given. N equal 5, 4, 3, 2. Let's consider this one as n equal 1, 2, 3, 4, 5. And then we have n equal infinity. Okay. We know that when we are drawing the energy level diagram, always the energy level gap should decrease. So this is n equal infinity in this way, right? So this is the energy level diagram that they have given. Try to understand energy level diagram. So they have given some electron transitions as well. What are the electron transitions that they have given? N equal 4 to 1. And n equal 3 to 2. 3 to 1. Yes. And then n equal 2 to 1. In this way. And then n equal 5 to 2. N equal 4 to 2. And n equal 3 to 2. Yes, in this way. And then they have given n equal 5 to 3 in this way, and then 4 to 3 in this way, right? So they have named these electron transitions as A, B, C, and these are F, E, D, and these are H, G. Got it? So these are the electron transitions that they have. So now What is the first question they have asked? Draw the corresponding spectral lines for above 8 electron transitions in emission spectrum in following diagram. So this is actually, we know that this is energy level diagram, isn't it? This is energy level diagram. In theory class, I taught you how to draw the spectral line diagram, corresponding spectral line diagram, when they have given energy level diagram, right? So this, if you consider this diagram, actually, we can see that the diagram that I taught you is opposite of this one. That means a mirror image of this one. That means if you consider this diagram, can you tell me for which direction the frequency and the energy increasing? To which direction frequency and energy increasing? Can you say from left to right or right to left? Frequency is increasing. Right to left. Right to left. That means for this direction, right to left, frequency and energy both are increasing. Then what will happen to the wavelength lambda? Wavelength lambda decreases for the same direction. That means right to left. Then keep that in your mind and draw the spectral line diagram. How we can draw the spectral line diagram? Recall what we learn in the theories, right? Spectral line diagram can be drawn in this way. Line diagram. Look at this one. Spectral line diagram. Now, in this way, same line, use the same line in this way. Here the gap is a little bit increasing. And what about this one? Yes. Here gap is a little bit increasing. Okay. And here, if you have drawn this kind of a diagram, you will be given marks. Okay. So this is the spectral line diagram that we can. Okay. Are we clear? This is the spectral line diagram. Now, the next question, label each lines as A, B, C, D, E, F, G and H in diagram 2 showing the corresponding electron transitions. Very easy. That's very easy. You know that this is actually correspond to A, B, C. But remember students, look at this one. Did you notice that? I told you that frequency is increasing for this direction. But according to the diagram that they have given, the frequency is increasing for the opposite direction. Did you notice that one? Right? According to the given diagram 2, they have mentioned that clearly frequency is increasing from left to right. But in the energy level diagram, we know that frequency is increasing from right to left. That means you have to that means you have to draw the mirror image of this one. Your spectral line diagram should be like this. Look at this one. So we have to be very careful. We have to be very careful when we are drawing the spectral line diagram. It's okay. Now look at this one. So first of all, we know that the lowest frequency belong to G. So they have given the frequencies increasing for the other way around. That means left to right. Then G should be drawn here. So this is G. I'll use another color for this one, if not. Confusing. Yes. This is G. Then we can draw H. Got it? Then we can go for the next series. D, where we can draw D. D. And we know that when frequency increasing, what will happen to the lines? Lines are approaching to each other. That means the lines are getting closer to each other. So this is actually D, E, F. Frequency increasing for this direction. And the next one. Look at that. So the next one is what? Which line should come there? C. C. we have to put here a large cap. Okay. C, B, A. In this way. G, H, D, E, F, C, B, A. This is the spectral line that corresponds to the electron transition from n equal 4 to n equal 1. So as you can see here, the highest frequency or highest energy belongs to the electron transition from n equal 4 to n equal 1. So that line has the highest frequency. So therefore, you should be able to draw this diagram in proper. Okay, right. So they have asked to label us this one. So in this way, we can label. And in this diagram, we can say that energy and frequency increase for right hand side from left hand side. That means the lambda wavelength is decreasing for the same direction. Right? Easy, right? This is not difficult. Hydrogen emission spectrum that we learn. This is hydrogen emission spectrum we learn. At next, they're asking, fill in the table. Name of the line series, ABC. ABC line series is representing which series actually in the hydrogen emission spectrum? Yes, Lyman, right? Remember, all the electron transitions are falling to the first principal energy level. So therefore, ABC belongs to Lyman series. And region corresponding to the electromagnetic spectrum, ultraviolet, UV region, ultraviolet region. Okay. Next one, DEF. DEF means actually all the electron transitions are falling to the second principal energy level. If it is to the second principal energy level, we can consider this one as the Balmer series. Balmer series, we can consider they are belong to, the lines are belong to visible light region. Visible light. Visible light region. So the next one, all the electron transitions, G and H, they are belongs to the third principal energy level. So that means we can say that Paschen. This belongs to Paschen series. Paschen series belongs to IR, infrared region. Okay. So this is actually a very small thing we have learning first unit. Easy, right? This is not difficult. This is very easy. Right, okay. Problem number 5. Calculate the frequency of the line which has the least frequency. If the energy levels 1, 2, 3, 4, 5 are given as minus 1300, minus 1312, minus 328, minus 146, minus 82, and minus 52.5 kilojoules per mole respectively. Right, they're asking calculate the frequency of the line which has the least frequency. Right, so put in the chat box your answers. Which line has the least frequency? Quickly, all of you put the answers in the chat box. Which line has the least frequency? Yes, good. Mariam, Asma, Sinet, Sinet Magarek, yes. What about the others? Right, okay. So we know that the line G has the, not A, the line G has the least frequency, because we know that for this direction, that means if you analyze the energy level diagram, in energy level diagram, which line has the least frequency? This one. The highest frequency belongs to n equal 4 to n equal 1. So therefore, let's consider G spectral line energy in energy level diagram electron transition, n equal 4 to n equal 3. So that is the electron transition. Electron transition from n equal 4 to n equal 3. Then what is the energy value for n equal 4 and what is the energy value for the n equal 3? And let's calculate the corresponding frequency for that energy gap, right? Let's see. In this question, now we have to calculate the frequency of the least energy gap, right? Look at this one. N equal 4. They have given the corresponding energy for the n equal 4 as, what is it? Minus 82 kilojoules per mole. And what is the electron energy for the third principal energy level? Third principal energy level energy is given as minus 146 kilojoules per mole. Right? According to the energy level diagram that we have drawn, we know that the electron is actually electron is moving from n equal 4 to n equal 3. And this belongs to Paschen series. And this electron transition has the least energy gap and the least frequency, right? Therefore, we know that how to calculate the energy under the electromagnetic spectrum. Under the electromagnetic radiations, we have learned how to calculate the energy. How we can calculate it? Equal HF H nu. If not, we can tell equal Hc over lambda, right? So this is actually energy of a photon. But remember students, since they have given the energy corresponding to 1 mole, we can rearrange this equation by multiplying Avogadro number. Then this is actually representing energy of a mole. Got it? I taught you these things, right? In the first unit, we have learned this one. Equal H nu means E represents energy of a photon. If you want to calculate the energy of a photon mole, what you have to do? You have to multiply that one by Avogadro number. So how did you identify the energy that they have given is related to energy of 1 mole? Look at this unit, kilojoules per mole. Kilojoules per mole. That means they have given energy for 1 mole. They have given energy for 1 mole. So therefore, you have to understand, we have to rearrange the equation before we calculate the frequency, right? If you forget that, definitely you won't get the correct answer. Keep that in your mind, right? Okay, now in here, what is the energy that we have to put? We know that electron is moving from n equal 4 to n equal 3. Then let's take the gap between energies. N equal 4 minus 82 minus 146 kilojoules per mole with the unit. Got it? Energy gap, right? We know that actually each spectral line is representing energy gap between the energy levels. And what is the Planck's constant? 6.626 10 to the power minus 34 joules seconds. And frequency, that's what we are going to find out new. And what is the Avogadro constant? 6.022 10 to the power 23 per moles. Got it? Per moles will cancel off, right? Here, joules will cancel off. But remember here we have kilo. Kilo means 10 to the power 3, isn't it? First of all, let's simplify 142 minus 82. What is the gap? 4, 64. Ne? That means 64 into 10 to the power 3. Okay, into 3. Then look at this one. We know that here the remaining unit is second. Ne? And the next thing is we can simplify 10 to the power values also. But let me take 6.626 and 6.022 together. And 10 to the power values becomes 10 to the power minus 3423. What is the gap? 111. That means 10 to the power minus 11. And second is the unit we have, nu. That means nu equal 64 10 to the power 3 divided by 6.626 multiplied by 6.022 10 to the power minus 11. Second will come here, but we can take that one for the numerator as per second, if not hertz. Yeah, unit is correct because we are finding the frequency. Since we are finding the frequency, definitely the unit should be per second or else hertz, right? Then, and I told you small trick. Can you remember that? In first unit, when we are doing this calculation, I told you that the numerical value in the Planck's constant and Avogadro number, by forgetting the 10 to the power values, Planck's constant is numerical value is 6.022. Avogadro number is, sorry, Planck's constant is 6.626. Avogadro number is 6.022. This multiplication is equal to what? 39.9. So this is a small trick that you have to follow when you're doing the calculation. Okay. This decimal value in the Planck's constant, when you multiply it by the decimal value in the Avogadro number, that multiplication is equal to 39.9. Then nu equal 64 divided by 39.9, and here we have 10 to the power 14 per second or else hertz. And now do the simplifications and get the answer. What is the log value for 64? Log value for 64 is 640 80621 point. 39.9 is 6010. Get the difference, 2502, 0.2052. So antilog of 2052, what is the value? 2052, 16011, 1604. 1.604 10 to the power 14 per second or else hertz is the answer. So this is the frequency of the energy, that means a spectral line, the electron transition, which represent the least frequency, because they're asking calculate the frequency of the line which has the least frequency, right? So this is it. So it has to be 16 point. Let's see. Is it 16 point? This is 64. And this is 6.626, 39.9. And here also we have 1 point. And here also we have 1 point. So the difference is 0.2052, right? So therefore answer should be 1.604 10 to the power 14. Rifa? Yeah, that's it. Take it again. Okay. So this should be the correct answer, right? It has to be 10 to the power 8. Can you explain it, Akash, how it can be 10 to the power 8? Put it in the chat box. Tell me what is the wrong with the calculation ID. 10 to the power 8 එකක් කියනවා නම් මේ 11යි 3යි කපලා ඇති ෂුවර් එක. 11යි 3යි වල කපන්න බෑ මොකද -11 නේ තියෙන්නේ. ඒතකොට -11 කියන එක උඩට ගියාම ප්ලස් වෙනවා. ඒතර +14. Okay නේද? Any different answers? Right. Okay. Now let's move for the simple C part. So isn't 10 to the power 14 belongs to the visible light region? 10 to the power 14 belongs to the visible light region. So we have the frequency in 10 to the power 14. So remember, it is actually regardless what is the region here, because we are just finding the calculation here, right? So if it is 10 to the power 14, it should be actually infrared region, because we are finding here calculation for Paschen series. Paschen series actually belongs to infrared region. So visible light means the next one. It should have some kind of a greater frequency, 10 to the power 15. So if it is in the 10 to the power 15 range, that should be visible light region. Since this is 10 to the power 14, we can consider this one is what? Infrared region. Okay. This is not actually visible light region. This is Paschen series, infrared region. Number 4 question also missed, right? Number 4. Draw the electron transition. Go for the ROM number 4. Draw the electron transition relevant to first ionization energy of hydrogen in diagram 1 using an arrow label it as P. So when you are drawing the first ionization energy, how we can draw the line? Right? In the diagram, in the energy level diagram, they have given spectral lines as A, B, C, D, E, F, G, H. Likewise, they have given some lines. So before capital A, you can draw their P. That means first ionization energy of hydrogen. Right? We know that first ionization energy means what? The minimum energy that is required to remove one electron from the valence shell of hydrogen atom. Right? So that electron is going for the infinity. We are removing that electron from the atom completely. That means electron is going far away, infinity. So therefore, when you are drawing that energy level diagram, you can mention that one in this way. So this is n equal infinity. And this is n equal 1, 2, 3, 4, 5. According to the diagram that they have given, we know that this is the spectral line, that means energy electron transition form, n equal 5 to n equal 1. This is A. This is n equal 3 to n equal 4 to n equal 1. And this is n equal 3 to n equal 1. N equal 2 to 1. So therefore, A, B, C. Now they are asking to draw the energy level diagram. In the energy level diagram, the electron transition that correspond to the ionization energy of hydrogen, right? If you consider hydrogen atom, gaseous state atom, it releasing the one and only electron from the atom, and this electron is going for the infinity level. Remember, students, if they have asked about the ionization, definitely this electron is going for the infinity level. So that's why in this diagram they have given infinity. Can you understand? So therefore, look at this one. Draw the electron transition relevant to first ionization of hydrogen in diagram 1 using an arrow, label it as P. Right? So first ionization means releasing one electron from the atom. Releasing one electron from the atom. Remember, actually, the electron was in the first principal energy level. Students, you have to notice this one very carefully. The first electron, the one and only electron, was in the first principal energy level. And it went to the infinity energy level. So this is the first ionization energy. Right? Actually, the energy level diagram that they have given is related to the electron absorption or electron emission. This is hydrogen emission spectrum. That means electrons are coming back to the energy levels, lower energy levels. But ionization means electron is going for a high energy level. So therefore, when you're drawing this diagram, in this diagram, when you're drawing that electron transition should be like this. N equal 1 to infinity in this way. That means arrowhead should be towards the n equal infinity energy level, because it's going for the infinity energy level in the ionization energy. So this is actually T. Raise your hand who drew this electron transition properly in this way with the correct direction. Let's see. Sinetma, Rafa, and Supipi. Very good. Yeah, we have few more. Sachin, yeah, very good. Okay, very good, very good. Yes. That is the way, yeah? That is the way. If you put the arrowhead towards n equal 1, then that is wrong. It's not the ionization energy. That is actually the opposite of the ionization. That means electron is coming from infinity energy level to the first principal energy. It's not the ionization energy. Ionization means the one and only electron in the first principal energy level of hydrogen atom going for a far away, that means infinity energy level, n equal 1 to infinity. Right? Okay, so that is the Rome number 4. I missed that one. Yes, now we discuss that one also. So that is question number 1, part B. So that is a good question related to hydrogen emission spectrum. We don't know whether in your examination, in the structured essay paper, will they give this kind of hydrogen emission spectrum question? If they have given this kind of a thing, you should be able to answer this. Why? We have discussed so many questions, right? After 2011, I think they haven't asked any questions related to the hydrogen emission spectrum in the structured essay paper or essay paper. But anytime, we can expect that one. We don't know, still these things are in syllabus, right? If you have any doubts, put your doubts in the chat box quickly. Right. Okay. Now I'm moving for the part C. Let's see what they have given in question number 1, part C. They have given some compounds in capital A: graphite, ice, magnesium, calcium oxide, silicon dioxide, and iodine. Capital B: covalent bonds, London forces, hydrogen bonds, metallic bonds, and electrostatic interactions. Capital C: conductor, insulator, electrolyte. So we have to fill the table according to the given ABC examples. They have given which kind of lattice is that: homoatomic core, ionic core, heteroatomic core, metallic core, polar molecule, right? Right. It's like this. Number 1, homoatomic. Number 2, ionic. Number 3, heteroatomic. Number 4, metallic. Number 5, non-polar molecular. Students, correct this one. In your tutorial, they have given polar molecular. Correct that one as non-polar molecule. Okay. Correct that one as non-polar molecule. Right. Now, what is the corresponding substance for these given types of compounds? Homoatomic compound. Where we can see homoatomic compound among these 5 compounds? Which one is homoatomic? First of all, tell me what is homoatomic. Homoatomic means actually the same element is connected to each other. So therefore, the homoatomic one that we have is graphite. Graphite. But remember, they are asking here homoatomic lattice, right? So therefore, definitely we can use the graphite here. So now I saw that some of you told me that iodine also, but iodine can be categorized in a separate one. So therefore, let's take graphite as the main, right? What is the ionic compound that they have given? Ionic compound that they have given is calcium oxide. Heteroatomic. What is the heteroatomic lattice we learn? The main one, silicon dioxide. Silicon dioxide, in the paper class, we have discussed about silicon dioxide more, right? Forming 4 bonds, and it's forming a huge covalent lattice. Therefore, boiling point and melting points are greater than we expected, right? So those kind of things we learn. And which one is the metal here? Of course, it is magnesium. And who is the non-polar molecule here? Definitely, it should be iron. So these are the corresponding 5 compounds according to their characters. Now they're asking interaction of particles. Right. Now let's see what are the interactions. When you consider graphite, graphite means a mineral, right? Formed by one of the main allotropes of carbon is considered as graphite, right? So therefore, definitely the carbon atoms are bonded by covalent bonds. But remember, London dispersion forces are also there, right? Because in the list they have given London forces also. So intramolecular interactions are covalent bonds, intermolecular interactions are London forces. Therefore, we can consider both of them because they have given interaction of particles. They haven't mentioned whether it is primary or secondary. We can include both of them. So the primary interaction is covalent bond and the secondary interaction is London forces, right? Okay. Then the next one, calcium oxide. What kind of a force is that? Calcium oxide is forming ionic bond. Normally in ionic bond, we have what kind of interaction? Electrostatic attraction, because we know that these are ions. Calcium oxide is formed by calcium 2 plus ion and O2 minus an ion. So therefore, this is actually electrostatic interaction, not covalent bond, London forces, no way, hydrogen bonds, metallic bonds, no. So actually here, we have to take this one as electrostatic Static interaction. Got it? What about silicon dioxide? Silicon dioxide, covalent. This is the primary interaction present in silicon dioxide. And the secondary interaction is London forces. What about magnesium? Magnesium is, of course, that is a metallic bond. Yes, they have given metallic bonds. Metallic bonds. Then what about iodine? Yes, covalent bonds between iodine atoms. And then if you consider two iodine molecules, definitely there are London forces. We know that if there are covalent bonds, of course, the secondary interaction type that we can discuss here is London. But these London forces are very weak bonds, right? They are forming, breaking, likewise. Very instantaneous induced dipole interactions, right? Right. So these are the interactions. And they have asked here electric properties. C, electric properties. So this is very important. Whether it is a conductor, insulator, or electrolyte, right? Okay, first of all, let's consider graphite. Graphite, is it a conductor, insulator, or electrolyte? Conductor means what? Conduct means they can what? Transfer the thermal energy and the electrical energy. And insulator means they cannot conduct the electricity or heat. What does mean by electrolyte? Electrolyte means actually the cations and anions. Mainly in ionic compounds, we know that if you consider sodium chloride, sodium plus cation, Cl minus anion, these are ions. These ions are considered as electrolyte. Normally, when ions are dissolved in a solution, they are in the form of ionic form. So they can conduct the current electricity. So therefore, they are considered as electrolyte. If they are ions, definitely we can consider them as electrolyte, right? In an ionic compound, we know that sodium and chlorine is there, if you consider sodium chloride. So therefore, there are two electrolytes, sodium plus cation and Cl minus N, right? So graphite is actually what? Conductor. The reason is we know that graphite can pass the current electricity. So therefore, we can write here conductor. What about calcium oxide? As I mentioned you, we know that calcium oxide is made by calcium 2 plus cation and O2 minus anion. So ions are there. Since it is an ion, we can consider this one as electrolyte. Okay. Can't we consider this one as a conductor? Can't we consider this one as a conductor? Calcium oxide is a solid. No, we can't. Calcium oxide ionic compound is a solid. If they have given, we learned this one, right? Under the ionic compounds, under the properties we learn, the solid form of ionic compounds cannot conduct the electricity. But the liquid form or else aqueous form of that compound can pass the current electricity. So therefore, we cannot put here conductor, only electrolyte. So these simple things you have to keep that in your mind. Silicon dioxide, no way, no way. This is actually insulator. Next one, magnesium. Magnesium, remember magnesium is a metal. It can consider as electrolyte because it's forming magnesium 2 plus cation. We know that in metallic bond, magnesium is releasing 2 electrons. So the electrons are dissolving in the electron C. Those electrons are gathered and forming electron C. Then the cations are sinking that electron C. So therefore, that is what? Metallic bond. Cations are forming, therefore electron. Can they pass current electricity? Can they pass current electricity? What do you think? Magnesium. Can they pass current electricity? Yes, they can pass current electricity. So therefore, conductor. Because of the electron cloud, we know that electron C is there. Because of that electron cloud, they can pass the current electricity. Next one. What about iodine? Definitely that one is a insulator. So this is the first question that they have given in the 2016 Visakha Vidyalaya paper. Right, okay. Let's move for the next question. Question number 2. Questions from number 1, row number 1 to row number 5 are based on the molecule with molecular formula C3H4N2. The skeletal is given below. Draw the most acceptable Lewis structure. Okay. So this is the skeleton that they have given. NH, 3 carbon atoms are connected in this way. And here we have hydrogen, and here also we have hydrogen. C3H4N2. So this is the skeleton. Right. How we can draw the structure for this molecule? Lewis structure. We know that definitely this carbon and nitrogen should form a double bond, because carbon should form 4 bonds in order to satisfy the octet. So there are no options. So the only option is actually to form double bond here. 1, 2, 3, 4. Then nitrogen will get here 1, 2, 3, 4, 5, 6 negative charge. Got it? And here we can see that if I put double bond here, what will happen? How we can draw the most acceptable Lewis structure for this one? Negatively charged and I put double bond here. Anyone drive the structure for this one? Long pair to nitrogen, double bond between nitrogen and carbon, and plus charge to carbon. Can that be in this way? No, 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 no. We cannot put plus charge on carbon. Why? If you put plus charge on carbon, carbon won't satisfy the octet. Definitely, carbon should satisfy the octet. Understood? That's the thing. And the next thing is carbon cannot make 5 bonds. That's also not possible. And then how we can draw this one? Any other suggestions from you? Double bond between first and second carbon atom and lone pair to the nitrogen plus charge. Carbon nitrogen double bond. We cannot make triple bonds here, right? If you make triple bonds, carbon will exceed the octet. And here also cannot make. Here also not possible. Nitrogen, hydrogen also cannot form double. So this is the possible Lewis structure that we can draw, and we will have two negative charges. So this is actually big issue. Okay? This is the structure that we can draw. If we put one lone pair on nitrogen, what will happen? Nitrogen is not satisfying the octet. Remember, all of them should satisfy the octet. Okay? No, all the carbon atoms should satisfy the octet. If we put positive charge in this way, that is wrong. Okay, that means we can draw the structure in this way. Here positive and here we can put a lone pair. But the thing is, if you put in this way, what will happen? Carbon is not satisfying the octet. Then how this can be the most stable Lewis structure? It cannot be. Ne? It's not possible. I'm thinking whether this structure is wrong or not. Give me a minute, students. Give me a minute. Let's see. Let's check whether there is a compound like this. Right, okay, students, this structure is wrong, okay? There is a issue with the structure. I'll give you the skeleton, correct one. The skeleton is actually carbon, nitrogen in this way. And another carbon, nitrogen atom. Right, okay. Cut the skeleton that they have given and draw this. So the skeleton that they have given is wrong. Huh? Now try to draw the Lewis structure for this one. Right, now okay. Okay, we have some ideas also, let's see. But sir, total formal charge is giving -2, formal charge name. Shouldn't the overall charge be 0? Yeah, that's why I told you, right? That's why I told you, if I put a double bond here, what will happen? Here we have negative sign. So therefore, overall charge is -2. So it won't become 0. Right? So therefore, this skeleton is wrong. Okay, we cannot consider this kind of a skeleton. That's why I searched this one in Google. Actually, this is not the correct skeleton. The correct skeleton should be this one. Right? In the previous way, if I put here positive sign, what will happen? Carbon will get a positive sign, means actually carbon is not satisfied the octet. So it's not possible. I told you that when we are drawing the Lewis structures, the main important thing, the satisfaction is what? Satisfying the octet, exceeding the octet or satisfying the octet, right? So therefore we cannot in that, right? Prefer. So what if we put double bond between first nitrogen and the first carbon, and then between second and third? In this way. Then also we have issue like this thing. Carbon is satisfying the octet, carbon is satisfying the octet, carbon is satisfying the octet. But here nitrogen, 1, 2, 3, 4, 5, 6, 7, negative sign. 7 means actually 2 minus. So PP, can you understand the skeleton is wrong? Okay. Whatever you try, actually you will have a charge. Okay. So therefore, let's change the skeleton in this way. Correct that one in the tutorial. Quickly, the tutorial. Correct this one as NC CH2 and NCH2. All right. Now try to draw the structure. For this one, you can draw the correct structure. I will name the atoms in this way. This is the first nitrogen atom. This is the first carbon atom. Second carbon atom. Third carbon atom. And the second nitrogen atom. Right. Okay. Now you can try quickly. So when you are drawing the Lewis structure for this kind of a molecule, you can see that carbon and nitrogen is terminal. So therefore, we can put a double bond there. That means triple bond. Now the two more bonds, triple bond. So nitrogen will have a lone pair. So therefore, nitrogen is neutral. And carbon is satisfying the octet, nitrogen is satisfying the octet. Already this carbon atom is satisfying the octet. Therefore, we don't have to worry. Okay. And what about this one? Here we can make a double bond and put a lone pair, right? And then we can see that this is also satisfying here. Okay, right? Now we can draw the correct Lewis structure. Next question is draw the possible resonance structures for this molecule and comment on their stability given reasons. Again, we have a serious issue like this. Can we draw resonance structures for this molecule? What do you think? Can we draw resonance structures for this one? Yes or no? For this molecule? No. We can't draw the resonance structures for this molecule, right? So mentioned there, we can't draw resonance structures for this molecule. Okay. So there is a small issue in this question. Therefore, yes, we have these kind of answers, right? We cannot draw C3H4N2. Sometimes they might have given this one as C3H4N2 minus also. Right, doesn't matter. Okay, let's forget about that one. So this is the Lewis structure. We cannot draw any resonance structures. Okay, so therefore, no resonance structures. Please correct that one, the skeleton and this. Okay, right. Now they're asking Vesper pairs, electron pair geometry, shape, and the hybridization around the atoms that they have given. First of all, let's consider first nitrogen atom, first carbon atom, second carbon atom, and the third carbon atom. What do you think? How many Vesper pairs are there? VSEPR pairs. And then they have given EPG, electron pair geometry, and they have given shape and the hybridization. Right? So when you consider Vesper pairs around the first nitrogen atom, how many Vesper pairs are there? Look at this one. Vesper pairs means sigma plus lone pairs. So when you consider sigma plus lone pairs, here we have two Vesper pairs. What is the electron pair geometry? If it is two Vesper pairs, electron pair geometry is linear. What is the shape? Remember, nitrogen is terminal one. So therefore, we cannot discuss about the shape. What is the hybridization? sp hybridization. First carbon atom, how many Vesper pairs are there? Two. Electron pair geometry, linear. Shape, also linear. Hybridization is sp. Easy. Second carbon atom, the middle one. Vesper pairs are four. Electron pair geometry is tetrahedral. Shape is also tetrahedral. And the hybridization is sp3. And then let's move for the third carbon atom. When you consider third carbon atom, how many Vesper pairs are there? 1, 2, 3. Electron pair geometry is a trigonal planar. Shape also trigonal planar. And the hybridization is sp. In this way. This is the table that we have to fill. Right. So that is Rome number 3. Next one, Rome number 4. Which of the following atoms in the Lewis structures in part 1 shows higher electronegativity? Give reasons. When you consider first nitrogen atom and the second nitrogen atom, first one and the second nitrogen atom, which one is more electronegative? We know that electronegativity is depending on 4 factors: hybridization, formal charge, oxidation state, and the surrounding atoms. When S character increases, electronegativity is increasing. So here we can see that sp hybridization in the first nitrogen atom, and here we can see sp2 hybridization. So therefore, who is the most electronegative atom here? First nitrogen atom, right? We can tell that because of sp hybridization of first nitrogen atom. So that is the reason. If you want, you can write down N2 nitrogen atom is showing sp2 hybridization. And the next one, for second carbon atom and the third carbon atom. Among these two, which one is high electronegativity? Which one is showing high electronegativity? Second one and third one. What do you think? Second one, we know that hybridization is sp3 here, and here hybridization is sp2. Again, tell me which carbon atom has the highest electronegativity according to the hybridization? sp2. So therefore, we can say that third carbon atom is more electronegative than second carbon atom, because sp2 hybridization of third carbon atom. Easy. So you don't have to explain that one in detail, briefly, within one sentence, explain it. Easy. Okay. Right. Now in Rome number 5, again, you have to change the question. You have to change the question because we changed the skeleton. So therefore, let's change the question there. Rome number 5. Identify atomic core hybrid orbitals that participated in formation of bonds in above drawn Lewis structure in part 1. So therefore, let me change this one as N1 and C1. Second one, let me consider that one as C1 and C2. Third one, let me consider C2 and N2. So in the tutorial, you have to correct these things. Right. Now, when you consider first nitrogen atom, what is the orbital involved there? We can consider, because of the sp hybridization, if you want, you can consider this one as sp hybrid orbital, or else 2p atomic orbital, since it is a terminal atom. Got it? First nitrogen atom is showing sp hybrid orbital, or else 2p atomic orbitals. And what about the first carbon atom? First carbon atom is, that is definitely sp hybrid orbital. Okay, definitely sp hybrid orbital. Let's consider they have asked about the sigma bonds. Okay, if they haven't specified the bonds type, just consider that is a sigma bond. And the first carbon atom and the second carbon atom, sp hybrid orbital. And what about the second carbon atom? sp3 hybrid orbital. Second carbon atom and the second nitrogen atom. Second carbon atom, sp3 hybrid orbital. Second nitrogen atom is definitely that should be sp2 hybrid orbit. In this way, you can feel that orbitals involved in the formation of sigma bonds between the corresponding atoms that they have given. Okay. I told you that if they haven't mentioned the bond type, just consider they're asking about only the sigma bond, because always the priority should be given for the sigma bonds if there is a multiple bond. You can search this one in Google. Actually, this is the skeleton they have given, right? The proper one. The other one, I think they have given some kind of an anion, right? In this question, into 2 minus again. But it's okay, fine. So let's learn something from here. Doesn't matter. Okay, are we done? Shall we move for the next question? Right. Let's move for the last part in the structure essay question. Question number 2, part B. Consider the following compounds list that they have given: carbon dioxide, carbonyl sulfide, methanol, and methanol. Right? So they have given 4 compounds. Select the polar compounds from the list from number 1. Oh, that's very easy, right? First of all, let's draw the Lewis structures with the correct shape. Carbon dioxide linear molecule. And carbonyl sulfide, how it's look like. Instead of one oxygen atom in the carbon dioxide, one sulfur atom is connecting there. That's all. And what about methanol? Easy, CH3. OH in this way. Okay. And acetaldehyde, if not methanol, can be drawn in this way. Okay, now what do you think about this one? We know that when you consider carbon-oxygen bond here, the bond is polarized and dipole moment is creating for the both oxygen atoms towards the both oxygen atoms. So therefore, resultant dipole moment is 0. So therefore, this is considered as non-polar molecule. Right? What about carbonyl sulfide? Remember, students, in carbonyl sulfide, sulfur is 2.5 electronegativity value. Carbon is also around 2.5 according to the Linus Pauling scale, right? Oxygen is pulling electrons toward itself because oxygen is 3.5. Therefore, resultant dipole moment is not equal to 0. The molecule is polar. What about this one? Definitely, oxygen is pulling electron more than the others. Resultant dipole moment is creating towards the oxygen atom. Therefore, molecule is polar. What about methanol? Definitely oxygen is pulling electrons from two hydrogen atoms. Carbon is also pulling. So therefore the resultant dipole moment is creating towards upward direction, which is not non-polar. That means this molecule is polar. So actually here we have three polar compounds: carbonyl sulfide, methanol, methanal. These three are considered as polar. The only non-polar compound is carbon dioxide. Got it? That's very easy. Next one, Rome number 2. In Rome number 2, they're asking, mention the types of intermolecular interactions present in following compounds. Carbon dioxide. Students, we know that carbon dioxide is non-polar molecule. So therefore, dipole-dipole interactions are not possible. So the only interaction types are London forces, London dispersion forces. Next one, carbonyl sulfide. In carbonyl sulfide, definitely the molecule is polar molecule. Dipole-dipole interactions are created. Dipole-dipole interactions. Addition to that one, we can mention here London forces also. Got it? I told you that if it is a covalent compound, whether it is polar or non-polar, you can put the London forces as a secondary interaction. And the next one is methanol. In methanol, what is the specialty? You can see that in methanol, OH bond is there. This OH bond is reacting with another oxygen atom, forming hydrogen bonds. Right? Oxygens are connecting like this, hydrogen bonds. So we have hydrogen bonds between methanol molecules. Addition to that one, we can put London forces. So don't we mention here dipole-dipole interactions? No need, students. Why? Hydrogen bonds is one of the types of dipole-dipole interactions. So therefore, no need to mention that one. Hydrogen bonds are enough. Addition to that one, we can put London forces. What about the next one? Methanol. Methanol is actually not forming a hydrogen bond because OH, NH, FH bonds are not there. Only carbonyl group is there. But since it is polar molecule, definitely dipole-dipole interactions are existing. Dipole-dipole interactions are existing. And London forces addition to that. So these are the secondary interaction types that exist between the molecules. Molecular interactions. Okay, very easy. Okay, are we done? Next one, arrange the molecules in ascending order of their boiling points. Right. Now, we have to arrange these four molecules in the ascending order of their boiling points. Right. Can you tell me which one has the highest boiling point and what is the reason? Which one has the highest boiling point among these four molecules? Anyone? Yes, very good. The answer is methanol. Remember, students, if there are hydrogen bonds, definitely their boiling points are a little bit greater than the others. Now, if you consider water molecule boiling point is actually not much expected value. But the real value is 100 degrees Celsius because of the existence of the hydrogen bonds. So therefore, since among these four molecules, the only molecule that has hydrogen bonds is methanol, methanol is Methanol has the highest boiling point. And the least one, least boiling point, belongs to carbon dioxide. The reason is carbon dioxide is non-polar molecule. So the interaction types are London forces, the weaker bonds are there for carbon dioxide. Now we have to choose which one has the next highest boiling point after carbon dioxide, whether it is carbonyl sulfide or methanol. How do you decide that one? Right? For your knowledge, I'll give you the values. Okay, look at this one. Methanol is minus 21 degrees Celsius. You don't have to remember this one. I found these things from Google to give an idea about these molecules for you. Let's see. In this way. So these are the boiling points of the given molecules. Try to understand. Right? These are the boiling points of given molecules. Now, you may think like this, sir, carbonyl sulfide is polar molecule. Therefore, the interaction types are dipole-dipole. Methanol also a polar molecule. Second interaction type is dipole-dipole interaction. So therefore, both are equal. Then we have to go for the next factor, molar mass. But according to the molar mass, carbonyl sulfide has the highest boiling point. Ne? According to the molar mass, because carbon is 12, oxygen 16, sulfur 32. If you consider the molar mass should be 12 plus 16 plus 32, 10. Yeah, we have 60 grams per mole. Okay. Yeah, any doubts? So why methanol doesn't have hydrogen bonds? Right. You should not ask that question for me, because I told you that hydrogen bonds, how it is forming, right? Remember, in order to form an hydrogen bond, I told you that there should be an electronegative atom like oxygen, nitrogen, and fluorine, X. And it should be connected with another electronegative atom like Y also oxygen, nitrogen, fluorine. That means XH bond is compulsory. In methanol, do we have XH bond? That means an electronegative atom connected to hydrogen. Is there a bond like in methanol? No, ne? So therefore, there is not possible to form hydrogen bonds. Okay, right. Then what are the doubts we have? Right, okay. Now look at this one. So now we were discussing about boiling point. Now when you analyze the boiling point of carbonyl sulfide and methanol, so you're expecting that the carbonyl sulfide should have the highest boiling point because of its smaller mass. But we have some kind of unexpected value, students. The reason is electronegativity difference. Right? We know that carbon sulfur, we don't have that much of a difference. Because of this carbonyl group, we have difference 3.5, 2.5. So, but here also we have carbon, which is 2.5, oxygen is 3.5. Students, if I ask you, what is the hybridization of this carbon atom? Listen to this one very carefully. This is very, very important point. Look at the hybridization of this carbon, sp. What is the hybridization of this carbon? sp2. So which one has the highest S character? Carbon atom in carbonyl sulfur. Higher the S character, higher the electronegativity. Can you understand? That means carbon's electronegativity is much more expected than 2.5. Can be a little bit different. So therefore, carbon-oxygen electronegativity difference becomes lesser. Therefore, the dipole moment is becoming lesser. But when you consider carbonyl group in methanol, since this carbonyl atom is less electronegative, the difference is becoming larger. Therefore, dipole moment is becoming larger. therefore the polar molecule, the polarity is increasing. In methanol molecule, polarity is increasing. In carbonyl sulfide, polarity is decreasing because of the electronegative difference, right? So as I mentioned you, we think that 3.5 and 2.5 again, but this is increasing up to 2.61, right? So this is actually decreasing for 2.41. Then which one has the highest gap? In this molecule. Therefore, highest polarity belongs to this molecule. Then we can consider this one is the more polar molecule. So therefore, the highest boiling point go for this methanol molecule than carbonyl sulfide. Understood? Right? One more reason. Okay, so this is the main reason that methanol molecule has higher boiling. Okay, and the second reason is the shape. This carbonyl sulfide molecule is actually what? A little bit linear molecule, very small molecule. Progress. The spread is very low. But this one, a trigonal planar molecule, so the spread is a little bit greater. So that is also one of the reasons that carbonyl sulfide has least boiling point than methanol. Okay, so this is a little bit complicated. You have to understand this one in some questions. In the examination also, in some questions they are giving us to think about these things, right? I know that if dipole-dipole moment, dipole-dipole interactions are there, definitely you are going for the next factor, molar mass. But look at this one. Since there are two carbonyl groups, same groups, they have gone for the polarity, right? So here also carbon-hydrogen polarity also not much stronger. That means hydrogen is 2.1, carbon is 2.5. So therefore, they have ignored that one. That means they have only considered about the carbonyl group and here carbonyl group. They are electronegative difference. Because of that one, we can discuss the polarity. Okay, so this is the way of comparing that boiling point values. Can you understand what did I explain here? So this is a little bit difficult. Anyone has any doubts? Raise your hand who understood my explanation related to this question quickly. If you have any doubts, anything, please put your doubts in the chat box. I will explain you again. Aarti, Akash, Sarina, do you have any doubts? Aarti and Akash, do you have any doubts? So why didn't put dipole-dipole interactions to methanol? I told you, Akash, the reason I didn't put dipole-dipole interactions to methanol. Hydrogen bonds is one of the types of dipole-dipole interactions. That's why I put only hydrogen bonds, not dipole-dipole interactions. ඒ කියන්නේ hydrogen bond කියලා කියන්නේ dipole-dipole interactions වල එක type එකක්. ඒක නිසා තමයි මේ දෙකම දාලා තේරුමක් නැහැ. Always remember students, when you put hydrogen bonds, you don't have to put dipole-dipole interactions there, because hydrogen bonds is the one of the type of dipole-dipole interactions. Understood? Anything else before we move for the essay quickly? Right. Right, okay. Now, let's move for the essay paper. Let's quickly move for the essay paper. If you have any doubts, put your doubts in the chat box. Okay. Is it raining in your area now? No. Okay, good. Because some of you have some connection issues also. So we are moving for the essay paper, part B essay. Question number 3. In question number 3 also we have to make some we have to do some corrections. First of all, they have given capital M is a non-metal. That's wrong actually. That should be metal. Okay? Capital M is a metal. Correct that one. Capital M is a metal. And they have given that fluoride of capital M is a metal element present in 13th group of the periodic table. Fluoride of M contains 16%. So you should correct that one as 67.86%. Correct that one of fluoride. First of all, correct these two. Capital M is a metal, and then 67.86% of fluorine. මේ පේපර් එකේ පොඩි අඩුපාඩු ටිකක් තියෙනවා. හරි. පොඩි නෙමෙයි බරපතල අඩුපාඩු ටිකක් තියෙනවා. But anyhow, it's okay. Right. Okay, then they have given capital M is a metal element present in group number 13 of the periodic table. Fluoride of capital M contains 67.86% of fluoride by mass. Fluorine is 19. Calculate the relative atomic mass of M. Came up there. First of all, what are the group 13 elements? Put the answers in the chat box. What are the group 13 elements? Only 2. What about the others? Huh? In the third unit also we learned under the oxidation state rules. What are they? Tell me 5 elements in group number 13. Yes, Rafa, good, very good. Huh? Yes, I got the answer. First one is boron, aluminium, gallium, indium, and thallium. Boron, aluminium, gallium, indium, thallium. All of them are metals. But remember, aluminium is special. The reason is aluminium is amphoteric, right? Boron is considered as sometimes metalloid because it is in the, we know that, can you remember in the periodic table, the staircase that dividing the metals and non-metals in the periodic table. So therefore, sometimes boron is considered as metalloid, but others are completely metals, right? So therefore, at the beginning of the question, they have given non-metal. That is wrong. Huh? Okay. Now look at this. Fluoride of capital M contains 67.86% of fluoride by mass. Calculate the relative atomic mass of M. How do you calculate? Remember, students, if it is group 13 element, what is the valency of group 13? I told you. Under the structure and bonding, I told you that what is the main valency? Yes, the configuration is S2P1. So if S2P1 configuration is there, what should be the valency of group 13 elements? Valency is equal to 3. That means any element in the group number 13 can form maximum 3 bonds. The bonding capacity. Valency means bonding capacity. Aluminium trifluoride, boron trifluoride, boron trichloride, aluminium trichloride, indium trichloride, thallium trichloride, gallium trichloride. Valence is 3. Can you understand? Therefore, but we don't know what is the element, whether it is boron or aluminium or gallium or indium or thallium. So that's what we are going to find out. Then let me take this one as XF3. Okay. So we have to find out who is this X. They have given here mass percentage of fluorine in this compound, which is 67.86%. Then they're asking to calculate the relative atomic mass of capital M. Very easy. Let me take relative atomic mass of capital X is M. Fluorine is 19 into 3. So here they have given fluorine percentage 19 into 3 multiplied by 100%. Right? Now we have to find out M. We know that percentage symbol will cancel off. And we have 19 multiplied by 3. What is the answer? 2757. So therefore, 5700 divided by M plus 57. This is 67.86. Then do the cross multiplication. When you do the cross multiplication, I can take here M plus 57, 5700 divided by 67.86. Right? Use logarithm. Use logarithm. 57, 1, 2, 3. 3.570 7559 6786 678 8312 8316. Take the difference. 3 4 2 9 1. And now you can take the antilog. 9 to 2 43. 92 43 is 44. Answer is 44. Take the difference. 44 minus 57. What is the answer? 27. 27 grams per mole. Yeah, who is the element? Identify M giving reasons. Who is the element? 27 grams per mole is aluminium. So as the reason, you can give that aluminium has the relative atomic mass 27. That's why we choose aluminium, right? So therefore, identify M. M is aluminium. Since its relative atomic mass is 27. In chemical calculations, we have learned these things. Okay. Right. At next, they're asking, write down the molecular formula of fluoride of capital M and draw the structure to show its shape. So therefore, we know that this is aluminium trifluoride. Aluminium trifluoride Lewis structure. Draw it perfectly. Aluminium is surrounded by 3 fluorine atoms in this way. Normally, we consider that these kind of compounds are electron deficient compounds because aluminium is not satisfying the octet. Aluminium cannot satisfy the octet here by making bonds with fluorine. So therefore, these kind of compounds are considered as electron deficient compounds. And we can see that the shape of the molecule is trigonal plane. Trigonal planar shape. After identifying M is aluminium, you can use aluminium. If not, capital M is also. Because now I identified that capital M is aluminium. Then later we can use aluminium, doesn't matter. If you want capital use to capital M symbol, that's also. Right? Are we done? Right, next one. Draw the structure of compound when fluoride of M reacts with ammonia. Now you have to recall your memory that we learn about dative covalent bonds. Can you remember? Aluminium trifluoride reacting with ammonia to produce compound AlF3 NH3. Here nitrogen is positively charged, aluminium is negatively charged. Dative covalent. So you have to show that one, the structures, the correct Lewis structures in this way. Aluminium trifluoride, ammonia, right? We know that ammonia is a Lewis base. Ne? What does mean by Lewis base? Lewis base means the one who can give lone pair to a Lewis acid. What does mean by Lewis acid? Lewis acid means a compound like aluminium trifluoride, electron deficient compound. So they can gain electrons from the others. Lewis bases can give the electrons for others. Lewis acids can gain electrons from the others. So therefore, the structure is like this. NH3. Nitrogen is positively charged since it is a losing electron. Aluminium is negatively charged since it is gaining electron. Through a dative covalent bond, these two molecules are forming this kind of a compound, AlF3 NH3. Quickly draw it. Okay. So everything we learn, right? Everything we learn in the second unit and the third unit. I want to make an announcement that I sent you that message. We are going to start fourth unit and fifth unit parallelly from June 8th. Okay. Tell your friends also that we are starting unit number 4 and 5. Sir, can we can draw an arrow instead of writing plus and negative? Yes, that's correct. Some people use this kind of a notation also. So this is also correct. Huh? Arrow should start from ammonia, nitrogen, and that should go for aluminum because nitrogen is the one who giving electron, right? Right. Okay. Do we have any doubts in this question? Anyone, please? Niveshi, Aarti, Akash, Asdiya, Asma, Manugi, Sachin, Rafa, Ritaj, Sarina, Sehanti, Senanga, Sinetma, Supivi. Do you have any doubts? No. Good. Right. Okay. Good. Okay. Then, if you don't have any doubts, let's have a small break. After the break, let's start the remaining questions. Okay. Then, after the break, let's start remaining questions. Take a break quickly. Right, okay. Let's start. Next one. Question number 3, part B. An aqueous alcohol solution contains 64% of alcohol by mass. The molar fraction of the alcohol in the solution is 0.5. Calculate the relative molecular mass of alcohol. Right, look at this one. An alcohol solution contains 64% of alcohol by mass. The mole fraction of alcohol in the solution is 0.5. 0.5 means half. Right, let's see. Now we have alcohol solution. Alcohol aqueous. That was meant by alcohol solution. That means in this solution, what we have? Alcohol plus H2, water. Right? Then they have given that mass fraction, the mass percentage of alcohol is 64. That means students try to understand. They have given that in this solution 64% of alcohol is there by mass, and the remaining 36% is what? Can you understand? So therefore, when you consider the alcohol and water mass ratio, this is 64 and 36. This is mass ratio. How do you convert this one into mole ratio? In order to convert this one into mole ratio, you have to divide this mass by its molar mass. Let's take that one as M. Here 18. So therefore, this is 2. Therefore, this is 64 over M. So this is the ratio, mole ratio. Can you understand? So mole ratio. And they have given another data. That means mole fraction of alcohol is 0.5. Right? What does mean by the mole fraction? Mole fraction means total number of moles. Out of total number of moles, what is the alcohol moles? So this is equal to half. 0.5 means half. Then we know the moles of alcohol, moles of water. So therefore, we can tell that, right, according to this value, 0.5 is the mole fraction. 0.5 is equal to 64 over M plus 2, total number of moles. Out of total number of moles, what should be the alcohol moles? So we know that this is very easy. Look at this one. Rather than taking here alcohol moles, alcohol mole fraction, we know that if alcohol mole fraction is 0.5, what should be the water mole fraction? We know that mole fraction summation is equal to 1. That is the theory we learned. So therefore, mole fraction of water is 0.5. Let's use that one. That means here 0.5 is equal to, we are finding here mole fraction of water, 2 over 64 over M plus 2. Right? We know that 0.5 is equal to half. Do the cross multiplication. 64 over M plus 2, this is equal to 4. Then 64 over M is equal to 2. Then what is the value for M? M is 32. 32 grams per mole. Can you understand? Capital M is 32 grams per mole. So this is the molar mass of that alcohol? Can you understand? Do you have any doubts? Right? Got. You got the answer, right? Can anyone guess here? Anyone in this session? Can anyone guess the alcohol here? Let's see. Let's see how much far you know the chemistry. Now you have learned chemistry for 1 year, A-level chemistry, right? 1 year back, you started your A-level career. Yes, Rafa, correct. Very good. That's correct. What about the others? No, Sachin, no. That's not the molecule. Yes, Asma, correct. That is it. Actually, this can be ethanol, CH3CH2OH. Okay, ethanol. Because we know that here two carbon atoms are there, one oxygen and six hydrogens. So therefore 24, 30, 24 plus 16 is not ethanol. This can be methanol. CH3OH. 12, 16 plus 4, 32. CH3OH, methanol, the simplest alcohol that we have. Understood? Okay. Sachin, you are correct. You gave the correct answer, but Rafa and Asma, you both are wrong. Sachin, you are correct. Right? So the alcohol can be methanol. Problem number 2. Calculate the concentration of the alcohol solution if the density of alcohol solution is 0.96 grams per cubic centimeter. That's very easy. Very easy. Look at this only. Normally, we have done these calculations in theory class also. If they have given the density, how we can find out the molar concentration? They're asking the concentration of alcohol, right? What is the density that they have given? So we found that this is methanol. Now we are going to find out the concentration. Let's consider 1 cubic decimeter volume of this solution. Okay, students, we are considering 1 cubic decimeter. So therefore, since they have given the density should be multiplied by the volume. 1 cubic decimeter is equal to 1000 cubic centimeter. Then we are obtaining the mass. Mass of what? Mass of solution. But we need to find out the mass of alcohol. We know that mass percentage is given as 60, 64. Then this is the mass of alcohol. But our purpose, our intention to find out the concentration. Therefore, we need number of moles. Then divide this one by its corresponding molar mass, 32 grams per mole. 32 grams per mole. Right? And what is the total volume of the solution that we got? The total volume of the solution was 1 cubic decimeter. Right? Then we can see that cubic centimeter per cubic centimeter will cancel off. Grams will cancel off. 2 zeros will cancel off in this way. Right? Here we have 1, 2. Then the answer is 9.6 multiplied by 2 mole per cubic decimeter to 19.2 moles per cubic decimeter is the concentration of this ethanol solution. Got it? Try to understand. 19.2 moles per cubic decimeter. Okay. If you have any doubts, tell me quickly. It's very easy. Density multiplied by the volume, then we obtain the mass of the complete solution. Multiplied by the mass percentage, then obtain the mass of corresponding compound. Divide by the molar mass, then we got the number of moles. Since we know the volume, we divide that one by total volume, then get the answer. Right. Next one, part C. An alloy contains only magnesium and zinc. 1.13 gram of this alloy was completely dissolved in 20 cubic meter. That should be 20 cubic centimeter, okay, of 3 moles per cubic decimeter HCl solution. Calculate the mass percentage of zinc in the alloy. Right. So how do you calculate this one? Right. Anyone got the answer? Anyone here did the calculation for the part C? Right. Okay. Let's do it together then. Look at this one. Question number 3, part C. We have that an alloy contains magnesium and zinc. 1.13 gram of alloy was completely dissolved in 20 cubic centimeter. Correct that one as 20 cubic centimeter of the 3 moles per cubic decimeter HCl. Then magnesium and zinc both are reacting with HCl. Magnesium reacting with HCl to produce magnesium chloride and hydrogen. Zinc reacting with HCl to produce zinc chloride and hydrogen in this way. So they're asking, what is the mass percentage of zinc? In order to find out the mass percentage, first of all, let's find out the mass of zinc, right? We know that if I consider the mass of zinc as X, what is the mass of magnesium then? 1.13 minus X. Okay, because in this sample only magnesium and zinc contain. Got it? That's the way. Right. Then what is the magnesium moles? The magnesium moles will be, when you divide this one by its molar mass, 24 grams per mole, then you will obtain the number of moles of magnesium. When you divide this one by its molar mass, you will obtain the zinc molar mass. Magnesium and zinc molar mass. Then the answer here is 1.13 minus 6 divided by 24 moles. and here X over 65 moles. Right? Those are number of moles. Magnesium moles and zinc moles. Students, when you try to balance this reaction, you have to put 2 here and 2 here as well. What is the amount of HCl reacting with magnesium? What is the amount of HCl reacting with magnesium? 1.13 minus X divided by 24 into 2. Why into 2? Because the stoichiometry ratio is 1:2. Right? So therefore, the HCl moles are twice of magnesium moles. And then what is the HCl moles reacting with zinc? Again, twice of that one, 2x over 65 moles. That means we have found HCl moles using the masses of magnesium and the masses of zinc. If not, moles of zinc and moles of magnesium. Moles of magnesium and moles of zinc. Using them, we have found out what is the amount of HCl reacted with both zinc and magnesium. And addition to that one, they have given, look at this one, separately they have given, was completely dissolved in 20 cubic centimeter of 3 moles per cubic decimeter HCl. Separately, they have given HCl moles also. That means number of HCl moles will be concentration multiplied by the volume. 3 moles per cubic decimeter multiplied by 20 cubic centimeter. That means 20 into 10 to the power minus 3 cubic decimeter. Per cubic decimeter will cancel off. Therefore, 60 into 10 to the power minus 3. That means 6 into 10 to the power minus 2 moles HCl moles. Students, then easy, right? Look at this one. We found HCl moles in this way and the other way also. So these two should be equal. That means HCl moles reacted with magnesium and zinc separately, the summation, this summation is equal to the HCl moles that we found here. Now hereafter, chemistry is over. Simple maths. 2, 2, here 3. Okay. And what we can do in order to find out X. I'm going to multiply whole equation from 24 multiplied by 65. That means every term I'm going to multiply by 24 multiplied by 65. That means this is actually 65 into 1.13 minus 6 plus this is 24 and this is 24 plus 65 into 10 to the power minus 2. Right. Now do the simplifications. Okay. 24x minus 65x. When 113 multiplied by 65, the answer is 15, 1 here, 5, 6, 5. Summation 5, 14, 1. So therefore, 73.45. Okay. Do the simplifications correctly. And here we have, when you multiply 24 by 65, 20, 24 here 2, 14, 0651. Right? And this is multiplied by 3. 0, 18, 1, 16. 10 to the power minus 6 means 46.8. Do the calculations correctly. Find out the value for X quickly. Find the value for X. Put the answers in the chat box for the value of X. Everyone do the calculations. Kammal unna the calculations tikka. Right, okay, we have answer 0.65. Okay, let's see. Now here we have 65 minus 65 24 141. So therefore we can tell that 41x is equal to 73.45 minus 46.8. So the difference is 5, 6, and here 2. So therefore 6 to 26.65. Okay. Then x equal 26.65 divided by 41. Calculations are not easy, but yes, still you can do that one. You can try it. Doesn't matter. 26.65 divided by 41. 0, 266. What is the answer? Yes. Answer is 0.65. Yes, that's correct. Sachin, your answer is correct. Very good. Nimeshi, your answer is correct. Very good. So these are the answers. Yes. So this is the mass of zinc. See, this is the mass of zinc. So they're asking here, what is the mass percentage of zinc? They're asking what is the mass percentage of zinc. Then we can calculate it. Zinc percentage. Total mass is 1.13 gram. Out of 1.13 gram, 0.65 gram is zinc multiplied by 100%. So therefore, grams will cancel off. Then the answer is 65 divided by 1.1%. Okay. What should be the answer? 65 log value 1.8129, log value for 11.3, 0.531, which is 0 point. Then 8, 9, 5, 7, 1. 7598 antilog. 57.8, 57.51. So this is the answer for zinc percentage. Yeah, 57.5152. There you go. So in the sample which is containing magnesium and zinc, the percentage by zinc percentage by mass is 57.51. 57.51. Yes, that is the answer. Quickly finish this calculation. Raise your hand who understood this calculation. Quickly. Raise your hand who understood this calculation. Sehanti, Sarina, do you have any doubts? Right. I think Zainab, just now you joined for the session, right? Quickly complete the calculation. Let's move for the next question. After this paper, we have only one more paper in this paper book, and I'll send you the next paper book as well, paper book number 4, very soon. Okay. Quickly complete this calculation, and if you have any doubts, let me know before we move for the next question. Yes, let's move to the next question. In next question, we have to explain a few statements. Let's see. Question number 3, part D. Sodium chloride is a solid which has high melting point, while carbon tetrachloride is a volatile liquid. Volatile means what? Easily vaporizing. So therefore, it's volatile liquid. So we need to find out whether this statement is correct or wrong, first of all. Sodium chloride is a solid which has a high melting point, while carbon tetrachloride is a volatile liquid. Yes, it's correct. The reasons. Now we have to explain this one. How we can explain this one? Right. In this way. Sodium chloride is an ionic compound. Which is made by sodium plus cation and Cl minus anion. Sodium plus cation and Cl minus anions are firmly bonded by electrostatic attractions. We know that between sodium plus cation and Cl minus anion, what is the attraction? Electrostatic attraction. If you want, you can use here adjective as strong. By strong electrostatic attraction. But carbon tetrachloride is a covalent bond and it is non-polar molecule. Therefore, thus carbon tetrachloride has a molecule of carbon tetrachloride has only London dispersion forces. Let's consider weaker London forces. Since electrostatic attractions are much stronger than weak London forces, sodium chloride is a solid which has higher melting point while carbon tetrachloride is an volatile liquid. So actually the point here, what is the point we are using to explain this one? Interactions. In sodium chloride, we have electrostatic attractions between sodium plus and Cl minus. So these are actually what? Very firmly bonded electrostatic attractions. But when you consider carbon tetrachloride, that's a covalent bond. And addition to that one, that is non-polar. So therefore, the between molecules, the interaction type is London forces. So therefore, we can consider that these electrostatic attractions are much more stronger than weak London forces. So therefore, sodium chloride is a solid which has high melting point than carbon tetrachloride. Carbon tetrachloride is a volatile. So in this way, we can point out this statement in this way. So if you want, you can add the new things here. New things means related to the statement. Don't everything that you know. Don't put everything that you know, right? So this is the first point. Are we done? Shall we go for the next one? Right. Let's move for the second statement. What is the second statement that they have given? Silicon dioxide is a solid with higher melting point, while carbon dioxide is a gas. Okay, we can explain in that way. So this is the way. Silicon dioxide contains strong covalent lattice. Can you remember lattice structure? Carbon dioxide contains covalent bonds. Silicon dioxide is polar, while carbon dioxide is non-polar. Therefore, interactions between silicon dioxide is dipole-dipole. And carbon dioxide has weak London forces. So weak London forces of carbon dioxide make it as a gas. The strong covalent lattice containing dipole-dipole interactions of silicon dioxide making it what? More powerful. That means that's a solid, right? Hence, silicon dioxide is a solid with high melting point, while carbon dioxide is a gas. So here also the main point is secondary interactions. Okay. Normally now in the examination, they are not asking these kind of statements, but who knows? Sometimes in your examination, they might ask these things. Third point is water is a liquid, but hydrogen sulfide is a gas. How do you explain that? Quickly complete this one. Quickly. Water is a liquid and hydrogen sulfide is a gas. How do you explain it? Problem number 3. Both molecules are polar covalent molecules. But water contains hydrogen bonds, while hydrogen sulfide contain only right. Okay. Shall we move to the next one? right? So the next statement, what they have given. Melting points and boiling points decreases down the first group of in the periodic table, but melting points and boiling points increase down the 17th. Right. The first bullet point is first group elements are alkaline metals, while 17 group elements are non-metals. So that means in order to compare the metals and non-metals, we have two different ways. The melting points and boiling points of metals should be compared in different way. For the non-metals, another way. So therefore, if you consider metals as group elements, they are forming metallic bond, right? So therefore, metallic bond strength first group elements decreases from top to bottom. Because we know that lithium, sodium, potassium, rubidium, cesium, which one has the highest metallic bond strength? Lithium. Reason, we know that down the group radius is increasing. When the radius increases, what will happen to the metallic bond strength? Decreasing, right? So therefore, we have learned those things, right? So therefore, metallic bond strength of first group elements decreases from top to bottom. Therefore, thus melting points and boiling points of first group elements are decreasing accordingly. For non-metals, how we can compare the metallic bond strength? For the non-metals, how we can compare the boiling points and melting points? From their size, from their molar mass, right? So if you consider group 17 elements, in group 17, atomic radius increases down the group. Therefore, size, that means the radius, increases, and molar mass also increases. Hence, melting points and boiling points are increasing. accordingly. Okay, so those are the explanation for the 4 statements that they have given. Right, quickly complete this one. Right, okay. So what are the doubts you have, students? Anything you want to ask? Please raise your hand who understood that everything we discussed today quickly. Right, okay. So then this is the we have one more question to discuss in this paper, Visaga Vidyalaya paper, and in the next class we can start the last paper. Right, so in the next month actually we have to do the next paper book 4 also. I'll send the papers, the paper book. So we are almost ready for the first term test. Actually, some of you have written the term test, right? So therefore, uh, keep in touch with these things, continuously do these questions, and if you have any doubts, let me know. And the main thing is I want to tell you that next month we are starting unit number 4 and 5. So in future papers, you will see that unit 4 and 5 questions are also included. We are going to discuss those questions also, especially gas laws, enthalpy. Very interesting calculations are there. You must do those questions because those are very important. So those are the calculations actually improving your calculations part in chemistry, right? That means they are related to chemical equilibrium like lessons also. So therefore, please do these 2 lessons properly and let's prepare for the exam questions, right? Okay. Then previous class recording, I will upload that one. So today recording, definitely I will upload that one today. If not, actually, if I take time, actually, we don't know what will happen to the recording, right? So therefore, I will upload it today. Right, okay. Then let's meet on next Monday. Next Monday. Until then, bye bye. Have fun. Goodbye, also.